All right. Good afternoon, class. Welcome to Cryptography 102. You will get extra credit for being here. There will not be a pop quiz. My name is Eli. I will be your professor for the next hour. And this is Rendle. They do something to do with computers.
I'm a TA.
You're my TA. You're my TA for this session.
Yes, I never even went to school.
So one of the greatest pieces of art I think ever made, Pacific Rim, has a line in it that says, "Maths is as close as we get to the handwriting of God." And I would like to share some of that with you here today, and then Rendle's going to do some code or something.
Yes.
It's going to be great. So cryptography, we all know what cryptography is. Hiding things, making secret text, right? Using mathematics to share secrets. And today we use a lot of cryptography in the internet running.
Yes.
Elliptic curves and all that good magic, and then quantum computers is going to change the game and
bank payments.
Exactly. We run on cryptography, but
Yes.
we often don't know how it actually works, and you can start looking at it, and it's all very complicated. But there are also some weird, fun bits in there, and that's what we're going to talk about today. So we have a bunch of topics that we can cover. We're going to let you pick what some of those are, because this is a class-led teaching environment. But we're going to start off with something that's actually already been covered at this conference. Who was in the Enigma machine talk yesterday? Anybody? All right. So please do heckle. Tell us things that we got wrong or were missing. But we're hopefully going to take a slightly different angle on it.
I know I am.
Sorry?
I'm pretty sure I am.
Oh, yeah, you are. God knows what you're going to do. So cryptography. Yeah, we're covering a smorgasbord of topics today. It's up to you. Here's some cryptography for you. NDC is great, but I don't want everybody to know that, because otherwise everybody would come and then there'd be no space left for the rest of us. And I want to be here. So I'd like to send that message as a secret. And what I do in order to encipher this is I just swap every letter with another letter of the alphabet. This is a Caesar cipher. And it was at one point military-grade encryption because it was used in the Roman military. So you turn NDC is great into that string at the bottom, which I'm not even going to try and pronounce. And what you're doing here is you're essentially considering letters as numbers, and you're performing a mathematical operation on them. So you're adding 6 to each, and then you're retranslating those numbers back into letters. This is very easy to break as a form of cryptography with letter frequency analysis, right? You can go one step further. You can say, adding +6, instead of adding the same number each time, you can add a different number each time. So you can use a private key, which also can be represented as a string of numbers. You have your secret message, you have your private key. You add those pairwise, modulo 26, because you've got 26 letters in the English alphabet. And then this is extremely secure, actually. But in order to use this as a method of cryptography, the other person needs to know your private key. And if your private key is as long as your original message, well, how did you share that with them secretly in the first place? Chicken and egg problem. And this is encipherment. This is symmetric cryptography. What you're doing here, if you have a private key and you're enciphering each letter differently every time, is actually can be considered as this is a Vignere cipher.
Yes.
This is, and in this case, they've used A as 0 rather than 1, so off by 1 error there, unfortunately. But every single time you encipher a letter, you need to take another letter to pair it with. So, for example, I would take S and I would add R to it, and I would come out with letter J. And if you do this for every single letter, it's actually secure. But then, you have the problem with the chicken and egg thing, where your private key needs to be shared in the first place. And you sort of build up more and more complex things, ways of using this over time, before we discovered asymmetric encryption. And the most famous usage of this was the Enigma machine. So who knows how the Enigma machine works? Okay, yeah. Right, in which case I might speed through the rest of this, and then we'll have more time for other things. So, clicker's not working. Yeah, the Enigma machine. You've got a rotor, and it steps every single time. This is cycling through the alphabet and encrypting each letter differently every single time, right? The first mapping that you do when you're enciphering your messages changes every single time that you press a key. And this is essentially giving you a private key, which is the alphabet in sequence. But we need to do more scrambling than that, so we add more rotors. So that's the 3 rotors that we just saw. In a lot of machines, they will have more than one notch here. So these are the notches that represent how frequently those rotors turn, right? And so you're mapping, you're doing this sort of polyalphabetic cipher multiple times, and you're sort of stepping through the alphabet of the way that you're enciphering it differently on every single keystroke. And obviously the way that these 3 rotors are positioned when you start typing your message onto an Enigma machine determine how the encryption is going to work. But we need more scrambling than that. And so what the Enigma machine actually does as well is it adds a sort of secret extra rotor at the end, which is called a reflector. And so you've passed your letters through these 3 rotors that have scrambled it, and then you pass it through the reflector as well. You map that S there, that you've turned a C into an S, you map that S back into an F, pass it all the way back through the same scrambling, but backwards. And in the reflector, a letter is never mapped to itself. You don't have any letter of the alphabet that is unchanged by the reflector. And that means that there is no letter enciphered by the Enigma machine that enciphers back to itself, right? It's taking a different path back through the rotors than it took forwards. Don't worry about it. That won't be a problem, I'm sure. That won't be that won't be useful in the cryptanalysis of the Enigma machines industry at all.
No, I mean,
don't worry about it.
Stupid.
Yeah. We need even more scrambling, so we add what is sort of another rotor at the front as well, except this one is configurable, it's a plug board, it's very, very cool. This genuinely did increase the security properties of the Enigma machine and made it very, very difficult to decrypt because you could configure these differently, without having to take apart your machine. And this was called a Steckerbrett, and most of the Enigma machines that were in use during the Second World War did have this. And so if anyone ever asks you what an Enigma machine is and how it works, you can show them this slide, which makes it all, of course, completely clear. So bits of history about the Enigma machine. They did have multiple models, and they were often had more notches on those secondary rotors than I showed there. They had prime numbers, or numbers that were co-primed to 26, so that you had a long cycle length of how long they would take to repeat through a cycle. That's something that comes up again and again in cryptography, the idea of modular arithmetic and needing long cycles. Polish mathematicians were very worried about getting invaded in the late 30s, if you can believe it, and so they had a particular interest in decrypting Enigma machines. They actually built some replica Enigma machine. A lot of the security properties of the Enigma encryption depended on nobody being able to ever physically capture one of the models, because as soon as you had one in hardware, you could analyze it fairly easily and look at what it was actually doing. So, physical security is always king, I suppose. But the Polish mathematicians actually built a replica and then brought it to the UK when, things all started to kick off. And that was a massive, massive help in the breaking of the Enigma machine. And tidbit, the US and the UK, allegedly, there isn't actually hard evidence for this. They allegedly sold and distributed Enigma machines to their allies around the world after having broken the encryption. I did a bit of digging on this, and it is it's only allegedly. But, yeah.
But they did.
Very probably.
I mean,
I'm not willing to get on stage on YouTube and say that with my whole chest.
But if you went on if you were able to go on the internet and find out that that was actually true, then somebody would be like in a basement underneath MI5 having their feet put to the fire going, how did that get on Reddit? Because we all know Reddit is the only place where you can actually confirm the veracity of things.
Oh, yeah, I mean, this is 2025. You've got to be adding Reddit to the end of all your Google searches now.
Exactly, yeah.
That's what I did, and I came up with that link, so please go and read it. The person who wrote that blog post actually has real sources, so if you want to read more, that's the place to go and do it. Enough from me. Let's go and look at some code. Rendle.
So, what happened was I submitted a talk to NDC Copenhagen on Zig. And because I've just discovered Zig, and Zig's a really cool programming language, and they didn't select it. And then Eli said, oh, do you want to do this talk with me, and you can do the code bits? And I thought, aha. So, this is my talk about Zig. This is the Enigma machine implemented. Glasses. So it is both. But I am learning Zig, and so I thought it would be fun to write some of these in Zig. And it did actually get to show some really quite fun stuff. So this is an Enigma machine, and Zig is like a replacement for C. So people say Rust is the alternative to C++, which is right, because it's insanely fucking complicated, and trying to program it hurts your brain and is probably bad for your teeth. Whereas C, despite the best efforts of people to mutate it over the last 55 years, has remained remarkably simple. And Zig is basically just coming along going, I'm going to be a better C. And so, yeah, it's very, very simple. We have an import up at the top here. We import std. Almost everything is under there. Config is another file that we have in our directory here. And we can see config. And yes, in here we have our plug board, which is a 26 element slice of U8. So Zig is so simple, it has no concept of chars or strings. So the closest it has is an unsigned 8-bit integer, a U8. And if you want a string, it's an array or a slice of unsigned 8-bit integers. And Unicode? No. So my Enigma machine will not encrypt emoji, or indeed letters with accents on, although the Germans, despite all their insistence that the accents and everything are very, very important, coped perfectly well without them when they were encrypting messages during the Second World War. Sorry, not the Germans, the Nazis. But yes, so, and then we have sort of various handy things. So we can do, we got our config file, so we go standard file system, current working directory, open file, and that gives us back a file pointer. And then down here we've got our config file, and we can just say read to end alloc. And this is the thing that I wanted to talk about in this particular thing here, not the Enigma machine, but the way that Zig handles memory, because if you're doing anything with kind of like text or opening files or any of this sort of stuff, you need to have heap memory. And in C, that was the old malloc, and you would malloc something, and then you would forget to free it, and then 13 hours later, your 286 tandem machine with 4 megabytes of memory that was supporting 8 users would crash with an out-of-memory error because you hadn't freed your malloc memory. So Zig, rather than just kind of like going, all right, we'll have malloc and it will mysteriously return a block of memory from somewhere, has the idea of explicit allocators, and you can create more than one. So instead of having malloc and then having to kind of track it across threads and everything, if you're doing multi-threaded, you can create an allocator on each thread, and it's a different chunk of memory. And then you can create an allocator just for a specific task, and then when that task is finished, you can destroy that allocator, and it automatically frees up all the memory that was associated with it. So even if the person consuming that thing forgot to free, you just go, no, that's it, boot the whole heap, and you don't leak any memory. And so you can see that here we have to pass in our allocator to get our config content, which is just a slice or an array of U8. And then here, this is something that Zig took from Go, and it's defer. And so it's basically at the end of the current scope, and in Zig it is the scope. In Go, I believe it's the end of the function, but in Zig it's the scope. And so anything you put in defer happens when you get to the end of that scope. So it kind of like goes out of scope. So we automatically make sure, so our allocate and our free are essentially next to each other. Anyway, so let's actually open up enigma.zig though. So yes, we have our, they're not objects, they're not classes, we just have structs, and structs can have methods here. So here we've got our Enigma machine, it's got 3 rotors, it's got a reflector, which is going to be 28 bytes, and a plug board, which is 28 bytes. We set a self to this for when we're doing sort of internal things. And then we have an init method. So this method doesn't have a first parameter of self, which means it's static. And so we can use this to create a new instance of the Enigma machine struct, and we just pass in rotors is undefined, reflector is undefined, and plug board is undefined. And so that allocates these on the stack. So it provides that variable space on the stack, but it doesn't fill anything with it, so we don't have to zero initialize it. And then
you're not a Python programmer, because you would have called that new rather than
I would have done, yes. Yeah. And then in it here, we set up our rotors with the wiring and the notch and the position and the ring setting, and then we create our reflector from the config reflector, and we create our plug board, and we have to int cast everything in the plug board for reasons that I can't remember, and then we set that into the machine, and then we have another public function which is just encrypt character. And so this takes self as its first parameter, which means this is an instance method on the Enigma machine type. And then we literally just, we go self.step rotors. And so what that will do is, can I go? Yeah, I can. Do you like the color scheme, by the way? Is it okay with everyone? Is anyone struggling to read that? Because I can change it to light, but I love it. It's called Blade Runner. And it's just, yes, sci-fi, but 1980s sci-fi. So yes, step rotors, and this was an interesting flaw with the Enigma machine. So the rotors will step by themselves, but also the middle rotor would get stepped by itself and then occasionally stepped by the next rotor as well. And this was another one of the bugs that helped Alan Turing and all his cohorts crack the code, was looking for that double stepping bug. It gave them a clue as to where which rotors were being used on a particular day. And so, because we want this to be authentic, we recreate the double stepping bug. So check if middle rotor should step, and if it's at the notch, then we say step middle true and step left true. So left is actually the last rotor, and right is the first rotor, because that's the way the Enigma machine worked. Sorry, I'll do that from your direction, so it went in at this side, over there, and then out that side. Stage, sides, and everything. And so, yes, rotor does most of this work for itself. We've just got our wiring and our reverse wiring, but everything is very, very simple. And then we have main.zig here, and we create an allocator. So we create a general purpose allocator, and that's kind of actually the general purpose allocator is the allocator. So that's the allocator that creates allocators. And then we say create an allocator, but we can also defer gpa.d in it. So that will destroy everything associated with that general purpose allocator. There are also different allocator types. So you have like arena allocators. There's even a diagnostic allocator for when you're trying to track down memory issues, and it will like write detailed information out to standard out while you're running your program, which is pretty awesome. And so yes, this will just read from standard in. And so if I go, I want a terminal. Nope. Well, hang on.
You're not going to show off the build pipeline?
And so we can do zig, build, run, and that. So yes, very, very simple. I'll show you how build stuff works, and then I should just be able to type things in here. And hello, NDC Copenhagen, and that comes out like that. And you can see how the Enigma, let me just zoom this in a bit so you can see. So yes, Enigma guaranteed that no letter would ever encrypt to itself, but what often happened, and what you got a lot of, is double letters coming out. So you can see it's done H and E both mapped to N there, and then H and A both mapped to O, and O and P both mapped to E. And so this, when they first started trying to crack the Enigma code, when they first saw this, they just assumed those were double letters, and they were trying to use their knowledge of words with double letters in those positions to crack it, and that caused them a massive problem. So anyway, that was Zig lesson number 1, and I'll pass you back to the person who thinks this is a talk about cryptography.
Cool.
Eli.
Give me back my slides.
No. They're my slides now.
All right. Audience voting time. I tried to build a ranked choice voting app, and the app's great, but I couldn't get the QR code to work. OK, here are the options for the rest of this talk.
Yes.
We will, show of hands, and we'll figure out which are the most popular, and then we'll go from there. So, who wants to know about hash functions? Yeah?
I promise you the Zig bit on that is really cool.
It's really good. Who wants to know about quantum computers? Yeah, OK. I think that's more than hashes.
I think we've got some of the not. Whose arms work?
Yeah.
Yeah, OK. All right.
Who wants to know about big prime numbers? Who wants to know about pseudo-random number generators and the blum-blum-shub algorithm?
It is just a cool name.
Yeah, right?
We do blum-blum-shub.
Let's do blum-blum-shub and then
All
Shor's
right.
algorithm, and then we'll see what else we've got time for.
Oh, hang on. We're going there, and then we're going back to here, and then blum-blum-shub, and then slideshow. There we go.
So full disclosure, this is in the talk because the name is funny, but it's also cool. So blum-blum-shub is an algorithm for generating pseudo-random numbers. Why do we care about having random numbers? Well, we've got lots of things that we can do with them, like statistical sampling for auditing things, like you want to randomly choose some records, and also for science. I actually work at a research institute, so I care about that.
And for allocating talk titles to presenters.
Yes, indeed, yes. Come to slide karaoke later tonight, it's going to be great. We also need them for one-time usage in cryptography. So for things like elliptic curve digital signature algorithm, you need numbers that you only use every one time that you actually generate a signature. If you don't do that, you can leave yourself open to attack. I think PlayStation, the PlayStation Store, had a hack because they were using the same number over and over again. And usage in one-time password systems, where you want to be able to produce a sort of consistent string of numbers that are predictable if you have the initial starting conditions, but are not predictable if you only can start inspecting the sequence midway through. Your clicker. So, how do we generate random numbers? If you want to do it properly, you need hardware. And this is hardware random number generators, or and this takes physical input from your environment. It will be like a temperature sensor, a pressure sensor, something like that. This is true randomness because the physical environment is unpredictable on a level that we can't, it's not feasibly predictable at all, basically.
There was that place that had a camera pointed at
lava lamps. I think it's Cloudflare. Yeah. Very, very cool. Love that.
But that is hardware random number generator.
Exactly. It's brilliant. This is not always feasible in some situations. Sometimes we want something that is cheaper and quicker to do, or we want it to be reproducible for some reason. And so instead, we do pseudo-random number generations, or PRNG. And this is using maths to generate random strings of numbers. And we need to know that they are random enough for use in cryptography if that's what we want to do with them. And that algorithm there, the xn plus 1 xn squared thing, that is the Blum-Blum-Shub algorithm. So how do we know if we're going to use pseudo-random number generators? How do we know if they're random enough for our purposes? This is the definition of cryptographically secure, right? Taking a sequence, if you've got your random number generator and it's spitting out some numbers, and you take a chunk of those numbers and you delete one of them, can a Turing machine in polynomial time determine what lives in that question mark bubble? Better than random chance. So if these are all binary bits, can it do better than a fair coin toss? And we say in polynomial time, if you came to Dylan's talk on algorithms, you'll know about big O notation. Polynomial time is anything that's n to a single, to a fixed number, rather than being, for example, exponential time. And if you can't get a computer to do better than random chance, how long would it take to do better than random chance? Because in theory, anything you could probably figure out the algorithm was generating these random numbers, but can you do it in a time that is feasible for an attacker to do, basically? And if it's cryptographically secure, it needs to be random enough, right? No polynomial time algorithm can inspect the output and determine what the next number in the sequence will be. And we also need to know, if they could manage to predict what the next number would be, they still shouldn't be able to reconstruct the numbers that came before. And this is backwards secrecy, essentially. Right. So here we have the Blum-Blum-Shub algorithm. And what this is it's, you have one number and you want to get the next number in the random sequence, and what it is that you just square it, take the modulus of some big number, which is the product of two primes, and then that's your next number. And after you take that number, you can take the last bit parity of it, you can take the last few significant digits. And the reason this is cryptographically secure is because it's really hard to know what things square to other things in modular arithmetic in general. That's a hard problem. The only way we know how to solve that problem is by factoring big numbers. This is called the the integer factorization problem. This is an NP-hard problem, unless you have a quantum computer. And there are some conditions that we need to satisfy in order for this to be a useful way of generating numbers. Your primes have to have certain conditions. They have to be a multiple of 4 plus 3, and that gives you that nice quadratic residuosity condition. And they also have a condition that need to be called safe primes, which are just a particular kind of prime where if you take one away and halve it, the number you get back out is also a prime number. And what this does is it maximizes the cycle length of this number generation. So just like having the notches on the Enigma machine be co-primed to 26 means that it takes a long time for things to start repeating, it's the same principle here. When you're working in modular arithmetic, you end up needing to use a lot of numbers that are co-prime, which means that they share no factors. So 17 and 26 are co-prime. They don't share any factors. But 12 and 15 are not co-prime because they share the factor of 3. Right. And when you've done, you're sort of spitting out all of these numbers. There are lots of things you can do with them. You take the bit parity, you take the last few significant digits of it, but you've got a stream of random numbers that you can do lots of cool things with. Let's have a look at some code.
Let's. It's incredibly hot up here.
It really, that's why I've ditched the jacket.
Yeah.
Great professor look, but it's not a great time, moisture-wise.
No. Not that committed to the bit.
No.
Right. Enigma, go away, blum blum shub. The editor, if you don't recognize it, is Z, which is, again, what all the cool kids are using. So yes, this is the blum blum shub algorithm.
Oh, Blum and Blum were married. There were two mathematicians who were married to each other.
Yes.
Shub, I think, was just third wheeling it.
Just the third wheel,
Yeah,
yes.
exactly.
So yes, this is the blum blum shub. This is quite simple to implement. So we have our current state, which is x, and we have our modulus, m, which is p times q, and then we just init our struct here. So this is what's called an implicit struct in Zig. So when we have a source file in Zig that exports constants or variables or functions directly, when you import that using import.zig, it will go into a sort of implicit struct that doesn't have a name. So you don't have to create a struct and export the struct. You can just, everything that's exported in the file will be treated as a struct.
Naming things is hard, so if you can avoid it, you know?
So yes, I mean, this is one of the other things about Zig is they're very much into simplicity and not having dozens of keywords and something. So when you import a file, you assign it to a const. There's no kind of like hash import or define or whatever. And when you assign it to something, it is assigned to a single instance struct. So yes, but in here, so we have our struct that we're exporting here, and we have an init here that takes our seed and our big primes, our p and q primes. And we just multiply p and q together, and then we ensure that the seed that's been passed in is co-prime to m.
Yeah,
what does
your x
co-prime mean?
It means it shares no factors.
It shares no
You
factors.
weren't listening. I said that about 2 minutes ago.
Yes, I wasn't. I was worried about what I was going to say. So yes. And then we can init, and then we just have our next thing here, and we just use mulmod, which is multiply and modulus. So we're going to multiply it by itself, and then modulo that against the result of our two big primes, product of our two big primes. And then we can return that, and then next bit generates a single bit. And this is the next thing that I wanted to show you, and what I'm going to use from this is that Zig supports completely arbitrary integer sizes. So you can have a U, and it can be a U8, a U16, a U32, a U64. It can be a U1, it can be a U17, which I really appreciate because that makes it like BS slang. It can be whatever you want. Something else was using a U5, and I was having to try very hard to stop it from doing that. So if you only want to deal with one bit, you use a U1. That is an unsigned one-bit integer, otherwise known as a bit. So yes, and then we can intcast self.x and 1 to whatever we want to do here. So this is going to shift us along by a single bit in our self, and then next we can get next float. We have fill bytes. So this just takes a list of unsigned bytes and then just randomly goes through and loops the
generator.
The generator doing self.next bit and adds this to the accumulator and drops it into the buffer. So our accumulator here is 0, and then we say b.star, which is our buffer, each one loop around here. This is a for loop. And in Zig, for loops are not like C or anything else. They're not for a number, test and then make it bigger or whatever. It is basically for each. So it's for each item in buffer, which in this case is an array of unsigned 8-bit integers. And so we get a pointer to each element in there. And then we can just say b.star. So b.asterisk, which dereferences and assigns. So it's saying assign the value of this pointer. So I quite like that syntax. It's much clearer than C's kind of ats and asterisks all over the place. And then, yes, down here we just have a couple more methods. These are sort of internal methods. They're not exported. They're not inside the struct. And so we do a mul mod, and we have as, and we can create a U128. You can create a U256. You can create, I mean, you don't, probably. I'm not sure what would happen, but it will try and cope with it. As, by the way, these functions which have got an @ symbol in front of them, those are what in Zig is called built-ins, and they're like compiler macros, but they're built into Zig itself. And so that's the way that you do casting in Zig. And so then we just return our result. And because we've got two 64-bit ints, we turn them into 128-bit, and then we modulo that against M, which is a 64-bit int, and then that gets int cast back down to U64. Int cast here, I don't have to say what kind of int I want it to be cast to, because I'm doing return, and we know what type the method is, and so Zig is able to go, right, so you want it cast to an unsigned 64. And then we just have is prime, which I'm not going to look at now because we're just about to go and look at something else. Last thing for this section is Zig is very hot on unit tests. It's so hot on your unit tests that you put them in the same source file as the code that you are testing. You can just put test blocks down at the end, and a test block is just here is test, here is name of test, open braces, and then code inside, like you would have in a main method or something like that. And we can do std.testing.expect, and we just have Boolean expressions in there. There are some additional methods. We have expect equal and so forth, but everything that's in there is testable. And so if I do Control D in here and cd /BBS, and I can say Zig build test, and that will build the blum blum shub and run all the tests. And we can do src/bbs.zig, and there you go. So that runs all the tests on there. You can create a test step. We're going to look at the build.zig in a bit, but you can customize the test handling in there. But all three tests passed. So each of those test blocks with a string name is treated as a separate test, and then you can have multiple asserts within them. If one of them fails, it'll show you the line at which it failed and the error message it failed with. There you go. Back to the choice of slides.
Shor's algorithm.
Shor's algorithm.
And I'm going to burst your bubble here because this is not going to be Zig code.
No, it's
because Zig
not.
doesn't have quantum computing yet.
No.
Yet. Maybe one day it will.
The fact that I've got code for it at all is frankly just something.
Right, who knows about quantum computing at all? Cool. I will want your opinions on my explanation of what the quantum phase estimation algorithm is. Who has heard that quantum computers are going to break encryption and we're all going to die and the world's going to catch fire? Yeah. Who believes it? Okay, well, hopefully this will settle your mind. Well, it probably won't settle your mind a little bit, but I have another talk that will, so, look me up on YouTube. Right, so, Shor's algorithm. All encryption is based off of hard maths problems, right? And pre-quantum encryption is based off of these hard maths problems. We already talked about the integer factorization problem, which is that if you've got a big number, it's hard to find the things that divide it. It's hard to find all of the things that divide it. The discrete logarithm and the elliptic curve version of that problem are sort of related. It's hard to reverse engineer modulo arithmetic multiplication is essentially the idea behind these. And these are different instances of how that crops up. And so integer factorization powers RSA encryption, and the elliptic curve discrete logarithm problem powers elliptic curve encryption and digital signatures. So if these hard problems are solved, suddenly our encryption doesn't work anymore. And in 1994, so over 30 years ago, a guy called Peter Shor published some algorithms for quantum computers. And we didn't have quantum computers in 1994, but he knew one day we would, and he theorized how they worked, and he published some algorithms for how to use them. And turns out they do work. We've built the quantum computers, and we have proof of concept that Shor's algorithm can work. So what is Shor's algorithm? Shor has had a handful of them, but the one that is known as the algorithm is basically giving us a way to, in polynomial time, so in a time that we consider reasonable for an attacker to be able to dedicate to solving a known problem, we can take a number n, and any number a between 1 and n, we can find the smallest number, the smallest power we have to raise it to, such that the result is 1 mod n, right? So let's say that our n was 15 and our a was 2. The smallest number for which that would be true would be 4, right? Because 2 to the 4 is 16, that's 1 mod 15. So what this, and that's a hard thing to do with classical computing. That is not quick to do. But with Shor's algorithm on a quantum computer, you can do it in polynomial time. How does this break integer factorization? Well, I've got a worked example. So let's say we have a big number that's made of 2 big primes multiplied together. 323, this is 17 times 19. And if you were doing RSA, for example, you would be using a big number like this, 2 big primes multiplied together. This is a small one because I wanted to be able to plug it into Wolfram Alpha and have it actually work. We're going to choose some number a that's smaller than this, and I picked 11. Shor's algorithm tells us, for free, well, in polynomial time, that the smallest number that we can raise 11 to, the power of, to get 1 mod 323 is 48. No number smaller than that gives us 1 mod 323. Now, we want to choose an a such that that number, 48, is even. If we try Shor's algorithm when we get an odd number for the power, we have to try again until we find an a that does give us an even number. This can happen about half the time. What we can do now is we can do the difference of 2 squares. We can say, okay, in modular arithmetic, 11 to the 48 minus 1 is 0 mod 323. 323 divides that number. So we can do the difference of 2 squares, the sum times the difference. And that means that either 11 to the 24 minus 1 or 11 to the 24 plus 1, there's got to be some shared factors there. Unless 323 is prime, it has some factors, and those factors are also represented in 11 to the 24 minus 1 and 11 to the 24 plus 1. Now, we know that 323 doesn't divide 11 to the 24 minus 1, because otherwise we would have got 24 as our smallest number from Shor's algorithm and not 48. So we know that some of the factors of 323 have to go into the other half of that multiplication, the 11 to the 24 plus 1, right? And we can check if there's a chance that 323 just divides that and we don't get any extra information, but there's a chance that only some of the factors of 323 go into that, and there's a cheap way to check that with classical computers. We can do the greatest common divisor. And if we do this, we can say, okay, we take the other bit, we know that there's some factors that are shared, and we can check if it's all the factors, and if it's not, we separate out some of those divisors. And in this case, that's true. We find that the greatest common divisor, the biggest number that divides both 323 and 11 to the 24 plus 1, is actually 17, not 323. And so we know that 17 must divide 323. You sometimes have to do a few shots of this by just like randomly picking a in order to get this algorithm to actually spit you out factors, but it can, it does that. That's a feasible thing to do if you have access to a quantum computer big enough and reliable enough to run Shor's algorithm on a number that's, of the size that you're trying to attack. So this breaks RSA. And there are other Shor's algorithms. So we've knocked out the integer factorization problem. This is an issue. RSA doesn't work anymore, but that's fine. We have elliptic curves, right? No, Shor wrote algorithms for those as well, which is terrible and bad, and all our encryption is going to go away, and the world's going to blow up. No, it's fine. We have post-quantum cryptography. It's fine. We found other hard maths problems to base crypto systems off of. I have a talk about it if you want to learn more.
The thing I love about the post-quantum cryptography is it sounds like sci-fi. It sounds like jetpacks and
it is witchcraft
and things.
Like learning with errors and lattice-based cryptography.
Yes.
It's very, very cool, and I don't understand most of it.
But it's in .NET 10.
Yeah. So in fact, yesterday...
the release candidate came out yesterday, and it's fully in there.
Yeah, Philip, I've completely forgotten his name, but he's done talks about quantum computing at NDC before. Huh?
Ekberg.
No, other Philip.
Oh, Philip W.
Yes. Released liboqs.net, the .NET wrapper for the liboqs C library, which has got implementations of some of the post-quantum cryptography algorithms that have been approved by NIST and are in usage now. You can enable them in Firefox, in Chrome, in Cloudflare, so on and so forth. We have these things now. Please use them. They're great. But I want to talk about why this works. How does quantum computing actually kind of work? And this is very hand-wavy, and those of you who actually know about this, be very interested to hear what you think of this explanation. Here we've got two qubits, right? And they're in a sort of, they're in superposition. They don't have values right now until we look at them properly. And we can entangle them, we can pass them through an H-gate. And now these qubits are entangled, and if I look at one, it will cause the other to also adopt a value, right? Then what we do is we hit one of them with a super secret magic laser that does some stuff to it and sort of rotates it. You can think of it as a kind of rotation, right? It causes one of the qubits to have different properties to the other, but it's not observing it, so we don't break the superposition, and these two things are still entangled, right? And then we look at them, and we say, okay, now they have some values, right? But the pink one is still all kind of wonky, because we hit it with the magic laser that did some quantum computing magic. And what we care about out of this result is actually the angle by which it ended up being rotated. And what we actually care about in terms of that angle is how many times do you have to use that angle to get back to where you started? How many times, like, how does that angle relate to, the full circle? And the reason this is not a completely sort of hand-wavy argument is because this is sort of a representation of when you work with complex numbers and you raise things to powers. You can write complex numbers as e to the I theta, where theta is an angle. And when you multiply them, it's like rotating them. And what we care about, so when I was talking about modular arithmetic and raising things to the power being really hard to do and reverse engineer in classical computing, this is what quantum computing is doing, is it's making that easy, essentially. But yeah, that's how quantum computers work. And you have a really good take about why you think quantum computers work.
So yes, there's kind of, that's how they technically work. It's very, very nice of the subatomic particles that we're using for qubits to rotate themselves at precisely increments of 360 degrees. But no, so the current theory as to how quantum computers actually work is they can represent all the possible states, all the possible answers, but only one of them can be right, and then they can just kind of break down to the thing that is right. And according to the many worlds interpretation of quantum mechanics, this is because the algorithm runs on an infinite number of quantum computers spread across the multiverse, and the one of them that gets the answer right then collapses the waveform for all the others, and all of them end up with the right answer. So they all basically just guessed, one of them guessed right, and then told the others across the multiverse with Dr. Strange going wee in the background.
How did it come about? Get out of my house.
Yes. That is legitimately
I love the crowdsourcing the answer from the multiverse.
It works, yes.
Yeah.
And it's when sort of the Nigel Farage from the place that got the answer right comes and demands money with menaces.
Yeah, and so that magic laser is the quantum phase estimation algorithm. Huh?
For stealing our quantum computation.
Yes. Cool, anyway.
We have code.
You have some code.
I do have some code. It's very
It's Python time.
This is weird. And of course it's Python, because why wouldn't it be Python?
You could have done in Q#.
I could have done it in Q#, but, so yes, there aren't a lot of quantum languages out there at the moment. The two that I know of are Qiskit, which is this Python extension thing, and the other is Q# from Microsoft Research. And the thing is, if you have created a programming language and you're kind of proud of it and it kind of works, but you'd rather most people didn't use it, just stick sharp on the end of its name, and then people will avoid it like it's the plague, and it will never get mentioned on Hacker News or anything. Start it with F, and the effect is even more. So yes, FQ#. For Q, no, never mind. So yes, Qiskit. Because of course it's Python, because that's what we do. The people who do this science stuff, they never learn to program, they can just do Python scripting. And so everything has to be put into Python for them to use. So we have pandas and NumPy, and which I still pronounce numpy in my head, like the heffalump from the Winnie the Pooh cartoons. But so yeah, we have from Qiskit.circuit import classical register, which is like a traditional computer thing, and quantum register. So, and I mean, they are talking about like registers in a CPU. So we have our classical register, which is like going to be A or B or whatever, and our quantum register, which is the same thing, but it's got a qubit sitting in it, or a collection of qubits. And then from Qiskit circuit library, we import the QFT gate, because quantum cryptography is all about gates. You get some numbers that are the question, and then you push them through a gate like so many sheep, and then on the other side of the gate, out comes your answer, and nobody
That's the
knows
magic
why.
laser, yeah.
That's the magic laser, so yes. And so what we are doing here is we are essentially mapping Python code and Python libraries directly onto the hardware of a quantum computer. So we're almost back to assembly language. We're sending machine instructions to a quantum computer. And it doesn't matter the type of quantum computer. Microsoft have got the new ones with the Majorana particles, named after a fascist, unfortunately, but hey-ho, he did invent a particle, and it turned out that Microsoft were able to make it exist. It's a subatomic particle that can't occur naturally, but it turns out if you're clever enough, you can make it. But then you've got others where they're using ions trapped in rings and all sorts of different ways of making them. And so Qiskit and Q#, and there are a couple of other languages, are just abstractions over that, but they're still they're more like C abstractions than C# or Java abstractions. So we have our adder circuit, and we get in our A and our N and our precision, and we build a circuit. So we're going to create an adder circuit, which is the thing we imported from the Qiskit Shor adder here. And from here, you can see again, we've got our quantum circuit and our register, and the library, we've got our phase gate and an X gate and another phase gate and a swap gate and a QT full gate, and it's all about the gates. And so if you think about these gates, these are kind of like the logic gates of classical computing, so and or and XOR and NOR and that sort of thing. And so when you, in 15 years' time, start programming for these quantum computers, you're going to have to relearn the whole of logic, because all of the logic gates that we have in classical computing, they are gone, and we are going to have, these are your new gates, welcome your new gate overlords, and good luck trying to work out what the hell they do. I will have retired by then.
They're just unitary operators, it's fine.
There's what operators?
Unitary.
Unitary operators. So I'm a unitary operator until I get a girlfriend. No, wait. Sorry, that was not right. Okay. Edit that bit out. I'm still, part of my brain is working on the app for the slides tonight, so yes. But yes, anyway, essentially, I don't really understand what's going on in here, and I think that's fairly obvious. But as much as I can break it down, it is to do with you have your quantum registers and your quantum gates, and you put things in your quantum registers, and then you apply quantum gates in the same way that you apply sort of machine-level instructions in assembly language, so like add or divide or whatever, and then you have your logic gates, except they have become these QF gates and C phase gates and everything else, and it's all to do with firing lasers at ions and getting them to spin. Yep. So yes. Any questions? Please direct them to Benjamin, whatever his name is, whose GitHub repository I stole this from.
So one point about this is that you have extra qubits that you sort of add to this algorithm to increase its accuracy, because we are living in the non-deterministic world of AI and so on and so forth. Quantum computers are genuinely and usefully non-deterministic, and one of the things that you actually need to do if you want to get a reliable answer out of them is sort of error correction qubits. And so that's one of the things that makes this difficult to do on quantum computers as we're building them. They're still really small, and they're still like, they decohere all the time, and there's obviously lots of advancements being made in different kinds of qubits that exist.
Yes. The more qubits that you add,
the better, the more reliable your results
the number of error correction qubits required at the moment scales exponentially with the number. So it's like 1 qubit requires 1 error correction bit, 2 qubits require 4 error correction bits, 3 qubits require 8, and so on and so on. And so you end up with more qubits, because the error correction qubits are also qubits. Fortunately, they don't require, anyway. But this is one of the things that the Majorana, the Microsoft research project, is slightly better at. The error correction, they are self-error correcting because of the way it's essentially a particle that's been pulled far enough from the other part of the particle that it's acting as its own antiparticle, and the antiparticle provides error correction for the particle. Go read the paper. It's really complicated, and I had to have somebody explain it to me. And 30 minutes after talking to them, most of it's gone again.
It's like when I learned about time crystals,
really
and I briefly understood it.
Oh, this is my other favorite thing about post-quantum cryptography, right? So there are two libraries, or two sort of algorithms, and they're distributed through the crystals library, crystals with a K, and one of them is called Kyber, after the Star Trek lightsabers, and the other is called dilithium, after the thing that the Millennium Falcon uses for propulsion. And I know that the Star Treks and the Star Wars
You've just upped the YouTube engagement on this video.
Yeah, the Star Treks and the Star Wars people, they love sort of when you merge their two things together and you get Han Solo meeting Gandalf. So
that's not what a time crystal is, though. So with quantum computing, there's a thing called the quantum cloning theorem, which means that you cannot duplicate quantum state, you can only transfer it, which makes it really hard to store memory, right? You can't like copy something, you can only cut and paste.
Yes.
And also, what do you store quantum state in? And there's a thing called a time crystal that they've made it. Somebody theorized it in like 2012, and then in 2021 they actually made it in a lab. And they're usually Bose-Einstein condensates.
Yes.
And they're things that have a repeating structure in time rather than a repeating structure in space. Like a space crystal is something where, like silicon, where it's got the same structure repeated in space, but a time crystal is its lowest energy state is one of repeated motion. Anyway, more weird quantum stuff.
It's an infinity stone.
Yeah, it's like a tesseract. Yeah.
Yeah. It's like the thing.
Anyway, we don't have one of those. I would love one of those as a prop for these kind of talks. But yeah.
Okay.
That was not in the speaker notes for this. We're off the edge of the map now. We have 8.5 minutes left. Do we want to look at, what was the other one that we wanted to look at that people
I wanted to show the SHA-256 thing because it's how those numbers are created.
That's a cool Zig thing. Let's give them that. Yeah.
Let's go back to here, and then we'll just run through this very, very quickly.
Right, so we've done actual encryption, we've done pseudo-random number generators, we've done quantum computing. We're now looking at hashing, which is a very useful thing in all sorts of computer science, and in particular for, we'll go through it. What you're doing when you take a hash of a digital object, you've got a big digital object, and for some reason you want to be working with a smaller digital object that still is representative of the big digital object, and you apply a hash function to make that happen. Now, what defines a hash function is that it's extremely sensitive to its input. If I change something about this digital object very slightly, I'll get a different hash out the other end. It should be cryptographically hard to reverse, so in polynomial time, I should not be able to take my small digital object and find something that, when put through the hash function, would give me that hash. And it should always result in an output of the same size. So a given hash function will always give you like a bit of 128 string, a string of 128 bits or 512 bits and so on. This makes it different to a compression function, which is used in the construction of most hash functions these days. This is what a hash function is. So, some jargon to do with hash functions. You'll sound clever if you remember this and it ever comes up. The smaller digital object that you get out of the end of a hash function is called a hash, or a digest. So we talk about message digests as a thing that you can use as part of various crypto and security systems. If we have two large objects and we put them through the hash function and they give you the same small digital object out of the other end, that's a collision. We talk about hash collisions. People are very worried that Git is going to have hash collisions because of the hash system that they use for generating commit hashes. That won't happen. They're very careful about it. And the function itself, the hash function, in the construction of SHA-256, one of the SHA-2 family of hash functions, the way that they're constructed is they take their input, the big digital object, break it up into chunks, and process them sort of independently, sequentially. And the way that is what that's called, firstly, why do we want to do this? We can use digests of objects to identify them. So Git hashes, you have a hash of a Git commit. You can use that to load the state of that Git commit. And also content addressable systems, which are not really that widely used anymore, but it's where you index an object under what its hash is of a given known hash function. The more common thing that we do with hashes is that we use them to verify that the large digital object is what we say it is. So if I've sent somebody a big file and they want to verify that it's the same file that I sent them last week or something, they could hash it, put it through the hash function, and double check that they're the same thing. Because hash functions are so sensitive to input. So they're used as essentially signatures. Right. The way that hash functions in the SHA-2 family are built is by the Merkle-Damgaard construction. Damgaard, Danish, local. He's a professor of head of the research group of cryptography at Aarhus. And the way that it works is you take what's called a one-way compression function, which is sort of like a hash function, except that it doesn't always output something of the same length. So what it does is it takes two streams of inputs of a fixed length, of a given length, and it outputs one, and in a way that is sensitive to both the input bits. And so you could either use this to take two 128-bit strings and turn them into one 128-bit string, or one 256-bit string, split it in half, combine them, get one out the other end. But the output is dependent on the size of the inputs, so you cannot use this as a hash function itself. What we do in order to use these to generate a hash function is you take your big digital object, you split it up into bits, you pad it to make it up to a length, the appropriate length, and then you take your compression function and you just pass it through again and again and again. You have to have some initial state to start with, which are some known constants. In the SHA family of hash functions, we use things like the cubic roots of the first however many primes, which is very cool. And then you just pass your thing, you take the first 128 bits through, your compressor function, you get 120 bits out, pass that into the next, just sequentially. Build up this sort of hash. And that's how that works. Tidbits, yes. Damgaard is Danish, very cool, local, great, national pride, all of that good stuff. There's ways you can attack these. They've got different names. If you have a given hash and you want to find something that will hash to it, that's a pre-image attack. That's very difficult to do. It is half as difficult to find two things that would hash to the same thing. That's called a birthday attack. Come talk to me afterwards if you want to know why it's called that, because it's a cool story, but I'm going to skip it for now. And these are actually patented, the SHA-2 family of hashes, but they're royalty-free, thanks NSA. Don't come after us for doing some live coding. Let's look at some code.
Okay. So, yes, I wanted to demonstrate one thing with this. As Eli mentioned, the magic numbers for SHA 256 are, in particular, are here. And so we have hexadecimal representation of these things just in a 64-element slice of unsigned 32-bit integers. So yeah, it's the first 32 bits of the fractional parts of the cube roots of the first 64 primes. So that gives us 64 numbers. The thing that's great about it, you could just have chosen 64 completely arbitrary numbers. You could have used blum blum shub to generate some and then written them down somewhere. If you then lost them, then that would be it. Everything that had ever been encrypted with that. So they use something where it can be recalculated again and again and again. So they're hard-coded in most libraries like this, but you could calculate them. It's quite an iterative process. It involves like 2,000 loops to find the cube roots of some of the bigger of the first 64 prime numbers. And so you don't want to be doing that every time you want to run an SHA hash. And this is where one of my favorite things about Zig comes in, because instead of doing that, we can import our magic.zig here, and then down here, we can say const k, and we're going to assign this, instead of to just this block here, which is like that, we can specify a block label here for this block, and then we can break that block with the results of magic.genConstants and pass in magic.cuberoot in here and magic.squareroot in here, because the initial hash is the first 32 bits of the fractional parts of the square roots of the first 8 primes, because your initial hash values, you need less of them. And then magic.genConstants, if we go into magic.zig, so this this is the same code that you would use to generate these constants at runtime. We have our pub fn gen constants here, and we're going to return a table which is, again, just a count. So count is coming from here. But you see we have this comp time keyword and comp time there. So what that means is that because all the values needed for these functions are constants, they're known at compile time. And so why would you repeatedly run them at runtime when Zig can run them once and just store the output into your binary? And so that's what's happening here. So the compiler actually, while it's compiling, calculates the first 64 bits of the fractional part of the cube roots of the first 32 bits of the fractional part of the cube roots of the first 64 prime numbers, and then just hangs on to them. It compiles them in. And so this, it's like a macro language, but if you compare it to the macro languages in things like C++'s STL, ATL, or Rust's hygienic macro language, it's certainly better than C's macro language because it is just Zig. It's just Zig where you know the parameters for the functions at compile time, and it runs at compile time. So it's the same thing, and it's this comp time keyword that tells us that both the parameters to this method are known at compile time, therefore everything else in this method has to be known at compile time, and then that can just get stored into here, and we don't have to worry about remembering this big list of numbers here. But yes, so there you go. That was what I wanted to show you for SHA-256.
Right, and if you want to know about Miller-Rabin primality testing, come and grab me later, and if enough of you tell me to do it, I'll do it at Slide Karaoke instead of doing anything else. We are over time. Thank you so much for coming. Please tell us what you thought
less
of
than
it.
a minute, though. That's not bad.
Yeah, it's not bad. For us, that's not bad.
For us.
Thank you so much. I hope you've been enjoying the conference. It's going to be, it's been a blast so far. Tomorrow's going to be great. Enjoy the party tonight, and thank you so much for your time and attention.
That's right.